everyone. Thank you for joining us today. My name is Chris Sensor with Data Physics, and today we're going to talk about setting up an auto power spectrum or APS test. Today we're going to talk about inputting test parameters, setting up triggering, and setting up the saves in the DP900 software. We are recording this, and the recording will be made available to participants afterwards, and as always, you can check the Data Physics YouTube page for previous recordings and some additional materials. We received some feedback that there was some maybe basic information that people would like to have, and we do have additional training seminars that are recorded and available. Please contact us at sales@dataphysics.com or me personally, chris.sensor@dataphysics.com, and my email address will splash up at the end of the presentation if you want to reach out for some of those additional training materials. So into the 900 software. As we see here, we're in the Manage Test tabs, and you can see in our previous seminars how the Manage Test is laid out and creating a test and all of that. So we're going to go right into this test I had previously created. Test and Channels tab we covered in previous seminars. So first thing in Auto Power Spectrum is to input your bandwidth and number of lines of resolution. And this is going to determine what the delta frequency is of your FFT. You can pick from the drop down in bandwidth to adjust the frequency of your FFT, or the 900 software has a feature where you can manually type in a arbitrary bandwidth that you might want to use to get a specific sample rate. For example, let's say you had 1600 lines and you want exactly 1 Hertz resolution. You can type that in accordingly. Now, the other feature we have here is to input these parameters in the time domain. So if you want a time window that's exactly 1¼ seconds, you can type that in, and that is what 1 block or 1 frame of data is going to be. And then you tell the software how many FFT points you're going to want in that block. So the block size is basically going to tell us how many samples are going to be in this block, and that influences the delta frequency and sampling rate necessary. We're going to go back to the frequency domain and maybe do the 1 Hertz resolution. The next thing to look at here is the Advanced tab. There's 2 things in Advanced here. Remove mean from x sub x. This is going to take your time domain data, and if it's offset, it's going to center it around 0, or whatever the mean of that incoming data stream is. So that's useful if you're looking in the time domain. And then we have our guard band ratio, and this is telling the software what Nyquist sampling frequency to use. In our typical kind of scenario in the digital world, go to 1000 bandwidth, you can see this. The sampling rate is 2.56 times the bandwidth. Nyquist theorem says that you need to have a max sampling rate of at least 2 times the bandwidth to avoid aliasing. So what this guard band ratio lets you do is do a true Nyquist if you want, and just do 2 times oversampling. What this really gets you is you can increase the max measurement bandwidth that you can get in the software close to what the exact sampling rate of the hardware is. But we like to keep this guard band ratio because it protects things like filter roll off and stuff like that. So moving on here, the next thing is the zoom measurement. And what zoom processing does is it allows you to take a limited bandwidth or narrow bandwidth measurement with a very, very high frequency resolution. So you still use the same number of lines, but only in this limited bandwidth. So you can see our delta frequency, 0.04 hertz, very, very fine frequency resolution. Windowing, I have a couple different options here. Windows are applied to the time domain data before it is converted to an FFT to avoid things like leakage in the data. And we have some additional materials, like I mentioned before, to talk about things like window leakage. I'm not going to delve into that now. That's a topic in and of itself. But we have different types of windows here: rectangle, Hanning, flat top, Hamming, and Kaiser-Bessel. And what you can also do is if you select from table, you can have different windows applied to different channels if you want to. Next, you input averaging here, and we have three types of averaging: stable, which is also called linear averaging; exponential. The difference between stable and exponential is that exponential is a weighted average, so that the most recent frame has more influence on the final average than the first frame does, as opposed to stable or linear averaging, which applies the same weight to each frame that is in an average. And then there's peak hold averaging, which allows the final FFT to show you what the peak values were at each frequency band for the entire duration of the test. For now, we're going to stick with exponential averaging, and we're going to tell the software to use 10 frames in an average. We do have a clipping reject box here. This automatically rejects any frames that come in that clip based on the signal coming in and what the range of the channels are set to. If you're having trouble where you're not getting any signal in, sometimes it's best to turn off this clipping and just see what's coming in. If you are clipping an incoming signal and you're at your maximum range, then likely your sensor is undersized for the measurements that you're taking. Next, let's talk about triggering. There are a whole bunch of different options for triggering. What triggering does is it tells the acquisition to start at a particular case, right? So a time interval, an input channel, a source channel, a TAC channel, or a manual where you press a button when you want to acquire start acquiring data. So most frequently used is the input channel triggering, so we're going to use that as an example. The next thing here is delay. Delay is what you might hear referred to as a pre-trigger, and what this does is it allows the trigger to take some data before or after where the trigger event occurs. So if you want a pre-trigger, you would put a negative delay. And there's a couple different options for how to specify that delay. Most typically, I like to do a percentage of the block. So this would take 5% of the block before the trigger event to try and capture something like an impulse or shock event. You have a little buffer beforehand so that you're not just capturing where it triggers, but a little bit before that. Next, you would specify which channel that you're going to use as a trigger, and so we'll pick an input channel, and let's say channel 1. And you can use different things like rising level, falling level, or entry or exit of a bound. And here you can pick what level, let's say 5, and then the units. We'll pick engineering units. So at 5 Gs, as a signal is increasing in slope, that's when this would trigger. And then hold off is a parameter that prevents the next trigger from happening before these parameters are met. So in this case, the software would take an entire block of a measurement, 100% of the block, before it allows the next trigger event to happen. If you are doing some type of overlap measurement or wanted to increase time between blocks to allow, let's say, your system to settle out in between impulses, you can increase this to more than 100%, or in seconds, minutes, or number of samples. There is another advanced button here, and this is pacing as start and stop events. Now, pacing is most typically used in conjunction with waterfall plots to save samples at intervals in a waterfall plot, but you can also use it with averaging to, for instance, save an average and then move on to the next set of averages. So for instance, if you have stable averaging and let's say 4 averages, you could set your pacing to averages complete, and then after we take 4 frames and make an average, the software would continue on to the next average. If you had your pacing off after you took 4 frames and did an average, the software would go into a standby state and you would want to hit start again before taking your next set of averages. There are other things like start and stop events here. Now, what you might want to do is a session trigger, where instead of triggering each individual block, you would start on a particular input channel. So you would set a trigger here, and let's say I want to trigger when my input channel 1 hits 5 Gs. And then what would happen is this would trigger the acquisition, and then it would take 4 frames, as opposed to triggering up here, which would take a trigger event for each frame that's captured into an average. And then we have stop events. This would be for, let's say, if you want to stop acquisition after a certain amount of time instead of manually stopping when you're done. So the last thing we're going to talk about is the Saves tab over here in Auto Power Spectrum. The Saves tab gives you some powerful options here. For instance, you can do dual saves. So let's say you want to save every frame, and then you also want to save your averages at the end. This will save each individual frame that comes in, as well as the running average at the end. So some powerful tools here. In many cases prior to this implementation in our older software versions, you had a choice of one or the other. And this gives you a lot of flexibility in how you're able to look at your data sets. The last thing to talk about in the Saves tab is exports, and these are automatic exports that are set up. You can do ASCII, UFF, MEScope, SDF, MATLAB, CSV. For now, we'll use ASCII as an example. Now, if I want to export all of my average auto power spectrum data, that's GXX, I can click that here and add that entire group, and you can see this is all of the signals. Now, perhaps I just want to save a particular time domain signal, for instance, or linear spectrum. I can click Add Signals and pick just channel 1, for instance. And then there's other things that you can change here as to what the software outputs. Do you want a magnitude in phase, magnitude, imaginary, real and imaginary, all kinds of different things here. And you can also adjust the scaling of the output as well as the signal. So let's say I want my export to be velocity instead of G's. I can do that here and set this to be displacement or velocity, or convert to meters or feet, or some other measurements. And then from there, you also have this options tab, and you can either save in the default folder or specify a particular folder to save your export to. You could also either separate the run folders or have it all in one folder. Couple different options for how that happens. And from there, you can go and hit run, and that loads the test in test. Initialize starts the test. And then you hit start. I'm sorry, initialize loads the test, and then start begins acquisition. And you can see here by the total number of saves that I'm saving each frame, as well as the averages that come in. And from here, I can hit stop and either restart the averages by hitting start again, or hit resume to continue the averages, or just end the test here. With all of our analyzer functions, there are shortcuts right here up on the screen to change certain parameters, like windowing or trigger parameters or bandwidth as we go. And then, well, perhaps I let this go a little too long here. I've got quite a number of saves that I'm exporting, but from there, end the test and pulls the data onto your PC and does the export. All right, that is our time, everyone. Thanks for attending. Our next seminar is going to be on the 29th of October, and we're going to talk about ICP check in the software. Please feel free to email me directly, chris.sensor@dataphysics.com, or visit us on the web at dataphysics.com. Thank you for your time, and have a great weekend.